Now we're going to get into the formulas. So before I introduce the new formula of Coulomb's law, it would be best if we went back to Newton's law of universal gravitation, which says that there's a force of gravity between any two objects that have mass. So we have mass 1 and mass 2, and it's multiplied by a constant. This is the universal gravitational constant, and it depends on how far apart they are from each other. So if we have mass 1 and mass 2, that distance r is the distance from center to center between them. So if any two objects that have mass have a force of gravitation between them, then there is a force of electrostatics that acts between any two objects that have charge. So the formula is K, which is a constant, times Q1 times Q2 over R squared. And what this formula says is that there's an electrostatic force between any two charges that are separated by a distance of r. And just like in this formula, r is defined as the distance between centers. So this k is a new constant, which is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. So the meter squared cancels with the meter squared, and the coulombs times coulombs cancels with the coulomb squared, and we're left with a force of newtons. But what happens if we put a negative sign in here? Well, really, this formula should have 2 bars and should be the absolute value, because it's up to us to figure out that if one is positive and the other is negative, that they will attract. And if they're the same, then they will repel. So don't worry about the signs, just use logic to figure out what direction they're going to move. So let's go ahead and do a problem where we have a proton, and this proton is 2 meters from center to center from an electron. So we have an electron over here and a proton over here. And the question is, what's the force between them? Well, in this, we can use F equals K Q1 Q2 over R squared. And that's electrostatic force. Sometimes this is called the Coulomb force, but it's the same thing. So let's go ahead and put our numbers in. So we would have Fe equals 8.99 times 10 to the 9th Newton meters squared per Coulomb squared times the charge of a proton, 1.6 times 10 to the minus 19th coulombs, and ignoring the sign of the charge, 1.6 times 10 to the minus 19th coulombs for the electron. And then we have all of that divided by 2 meters squared. And if you want to practice this, you can put this into your calculator. And what I recommend to just play it safe for order of operations reasons is to multiply the top and do this as a separate 2-step problem divided by the bottom number squared. So that gives us a force, and that force comes out to 5.75 times 10 to the minus 29th newtons. Now, what if they ask us for the direction of the force? Well, all we need to do is think about it using logic. The proton and electron will attract. So the force of the electron, the force on the proton will be to the right, and the force on the electron will be to the left. So we have Fe and Fe. These forces are equal, and that's why there's only one number in the equation. So let me just show you one last thing, and that is the value for K, which is on the reference table. It's called the Electrostatic Constant, and they give it here for you so you don't need to memorize it. So here's our formula that's given on the reference table, so we don't need to memorize it. But it makes sense, again, because it looks very similar to Newton's law of universal gravitation. And just remember that down here they tell you R is not the radius, but the distance between centers. So we know that our formula F equals K Q1 Q2 over R squared. If we're dealing with two objects and the only thing we're changing is R, then K, Q1, and Q2 are constants. So we can say that F is directly proportional to 1 over R squared. So what does a graph of y equals 1 over x squared? In math, we know that that will end up producing a graph that looks like a decay, which is like what you learned in chemistry. And that inverse square, which this is an inverse square law, shows us that when we double the distance out, that we end up with 1/4 of the force, and that decreases according to 1 over 2r squared would be 1/4, 1 over 3r squared would be 1/9, and so on, just like what we did before. The difference about these formulas is that in gravity, you can only get attraction, but with electrostatic force, you can get attraction, but you can also get repulsion. Why? Because two like charges will repel. So let's go ahead and do a couple of problems that are very common on tests. I'm going to spread this out so we can really see what's happening here. And let's say that the problem says that we double Q1. And the question is, what happens to the force? Well, if we double Q1, we're doubling just one thing on the top of this equation. So if we double this side of the equation, then this side will double. So what happens when we double Q1? The force will double. Okay, what about some other types of things that can happen? If we double R, what will happen to the force? Well, if we double R, we have a 2 down here. Remember that this is 2R squared, so this becomes a 4, and we have a 4 in the bottom, so if we divided this side by 4, then we divide this side by 4. What if we tripled it? Well, if we tripled it, then the force would become a 9th. This would become a 3, and the 3 squared would become a 9. Here's where it gets a little bit tricky. What if we cut the distance in half? Now, think about it from a logical standpoint. If we cut the distance in half, we move these two particles closer together, what happens to the force? Well, we know that the force has to increase, but the question is by how much? Well, a half becomes squared. 1/2 squared is 1/4. So we have a 1/4 here. But we can't leave this as divided by. So when we divide twice, that's the same as multiplying once. Or we could do it as fractions and multiply through by 4 over 4, which is 1, and these 4's will cancel, showing us that the force is 4 times as much. And that makes sense because the distance has decreased, so we would expect the force to increase. And we'll do one last example. What if we double charge 1 and double the radius? Well, doubling charge 1 is going to make the force go up, but doubling the radius is going to make the force go down. But remember that this is squared, so we have a 2 in the top and we have a 4 in the bottom, so the force will be decreased by a half. In this unit, we have 4 main formulas. We already went over this one, Coulomb's law. So the next 3, I'm going to talk about them all at once, and then we'll go into the details of each one. The first one is E equals F over Q. That's electric field equals the electrostatic force per charge. V is voltage or potential difference, which is equal to energy. W remembers energy. We can't use E because E is electric field over charge. And finally, I, the current flow, is the rate at which charge flows, Q over T. So here are our four formulas: E equals F over Q, I equals Q over T, and V equals W over Q. And let's take the electric field first. So, electric field is defined as F over Q. And we can actually put this little sign over this. It's not on the reference table, but that means it's a vector. In other words, the direction matters. The unit for electric field is the Newton per Coulomb. There's no name for that, so it's just left as Newton per Coulomb. And because it's a vector, we have to take into account that it's the direction of what? Well, you should remember this from before. The direction of the force on a positive test charge. So you have to memorize that. So let's do a simple problem. We'll put some numbers in. Let's say that we have an electric field to the right. So what does that look like? Well, it looks like this. We can put our arrows in to show the direction of the field. And let's say we have an electric field. We'll make up a number here to solve. The electric field is to the right, and it's 3,000 newtons per coulomb. What's the force on an electron? Okay, so to do that, we just use our E equals F over Q. And we throw our numbers in. 3,000 newtons per coulomb. And because it's an electron, we know the charge on it. That's 1.6 times 10 to the minus 19th coulombs. And we end up getting a force, if you do the math on that, 4.8 times 10 to the minus 16th. It's force, so it's measured in newtons, but it's a vector, so we have to define the direction. This is tricky. Remember that the direction of the field is the direction of the force on a positive charge. So a positive charge in a field to the right would produce a force to the right on a positive charge. But the question was, what's the force on an electron? Well, an electron in an electric field to the right will feel a force to the left. So when we do this, the answer is the force is to the left. So I equals Q over T. What is I? I is current. It is the flow. Think about the flow of water in a river. Instead of the flow of water in a river, current is the flow of electrons in a wire. So the unit Q over T, that would be coulombs over seconds, and this has a name. It's called the amp. The full name is the ampere, but it's usually abbreviated amp, and the symbol for that is just a capital A, so that's kind of logical. So let's say we try to solve a problem using this formula. We have an electric circuit, so this means some wires, and 15,000 electrons flow through this wire every minute. Find the current flow. Well, this is not Q. That's not measured in coulombs. So what we need to do first is convert 15,000 electrons to coulombs. So we know that there's 1.6 times 10 to the minus 19th coulombs for every electron. And we know that we have 15,000 electrons. So if we set it up like this, electrons will cancel and we'll be left with coulombs. And that comes out to 2.4 times 10 to the minus 15th coulombs. What is that? Well, that's our Q. So now we're ready to use I equals Q over T. So we have I equals Q over T. And what's our charge? Well, we just found that. That's 2.4 times 10 to the minus 15th. And our time was given in minutes, so we have to convert that to seconds. 1 minute is 60 seconds. So that gives us a current flow of 4 times 10 to the minus 17th amps. Finally, we have V equals W over Q. very tricky on this one because what is V? Well, V is three different things. It's voltage, and they switch these up all the time, so you have to memorize this. V is voltage. It's also potential difference, which is very common. But it's also potential drop. And potential drop is the one that's used least frequently, but you still should know all three. So voltage, potential difference, and potential drop is V. What's the unit? W is energy. Now, when we talk about energy, that can also be the work done. It can also be the kinetic energy gained, and it can also be the potential energy gained. But typically, it's just left as energy. And we know that energy is measured in joules, and that Q is measured in coulombs, charge. So a joule per coulomb has a name. It's called the volt. And the abbreviation for the volt is also a capital V. So if we write this as if we write this as V equals 4V, then this V is our voltage or potential difference, and this V is our unit, the volt. So let's go ahead and solve a problem. It says how much work is required to move an electron through a potential difference of 12 volts. Well, we know our formula is V equals W over Q. So we have a potential difference of 12, so we throw in the 12. We're looking for the work required. That's going to be our energy. It's an electron, so we know that the charge is 1.6 times 10 to the minus 19th coulombs. And when we do the math on that, we get 1.92 times 10 to the minus 18th joules. So pretty straightforward. But let's say that the electron was released. Now, think about this. Work is being done on it. So it's gaining some type of energy. Well, what it's gaining is potential energy. And we could think of it this way, as we have a large negative charge and we're moving it through a potential difference. So it's gaining potential energy. What would happen if we released it? Well, there would be a force on it that would accelerate it back in the other direction. So the next question is, if the electron was released, how fast would it be going? How fast would it be traveling? In other words, what's its maximum speed? So to do that, we're going to say that the work done turns into kinetic energy. Well, we know that the work done was 1.92 times 10 to the minus 18th joules. So we can say that kinetic energy is going to turn into 1/2 mv squared. And our work or energy done was 1.92 times 10 to the minus 18th joules is equal to, and here's something new. What's the mass of an electron? Well, on the reference table, they give you the rest mass of an electron right here. And also they give it to you for a proton and a neutron. But we just need the electron, which is 9.11 times 10 to the minus 31st kilograms, times our v squared. And when you do the math on that, you get a velocity of 2.1 times 10 to the 6th meters per second. Remember that they can do this work and energy for potential and also for kinetic. So all of that was very straightforward. We just had a single formula where we were given two quantities and asked to solve for the third variable. So what happens if they start to combine these? Well, something to pay attention to is that each of these formulas have something in common. They each have charge Q. So we could be asked to solve for Q in this part and then use Q in this formula, or solve for Q here and use it in this formula. I'll show you an example of this. What if we have an electric field is given, the force is given, the current is given, but they're looking for the time. So E is right there. They gave us E. And F is given, so they gave us F. But ultimately, we want to find time. The problem is we only have I. So if we only have I, we can't solve this problem. What do we need? We need Q. So we can use E and F to get Q. And then what can we do with that Q? We can bring it over to this formula, sub it in, and solve for it. So we could do this in many different combinations where maybe they ask you to solve for Q here, and then use that Q in either one of these two formulas. One last thing, I mentioned that V is equal to W over Q, and we know that that's energy, and that energy could be potential or it could be kinetic. But remember that energy is also power when we do it with respect to time. So power can come into these problems as well because they often use time. This is rare, it doesn't come up that much, but you should know that you can use these formulas in for your work, take the time, and calculate the electric power. There is a link in the description with these problems, so if you want to, give these a try first on your own to get some practice. Otherwise, you can just follow along and I'll show you how to do all of them. So let's read the question. How long does it take? What does that tell us? How long does it take? That's time. So we're looking for time. And it says for 25 coulombs. What does that tell us? Well, that's our Q. Q is 25 coulombs. And for an electric circuit, if 1.8 amps of current flows, so that's our value for I, 1.8. So we are going to use I equals Q over T, and we put in our 1.8 amps and our 25 coulombs for charge, and we get our time to come out to 13.9 seconds. So it's an easy, just one-step problem. So, next one, what is the potential difference? First of all, you have to remember that potential difference is voltage. So we're looking for our voltage, and it says between the terminals of a battery in which 4.32 joules of energy, so that's our W, 4.32 joules of energy are used to move 0.18 coulombs of charge, so that's our Q. Our Q is 0.18 coulombs, so that's just a straightforward V equals W over Q. And we can put in our 4.32 joules as our energy and our 0.18 coulombs for our charge. And when we divide those, we get a nice even 24 volts. The last one says a proton is placed in an electric field, so we know that that's E. So that's 3 times 10 to the 15th newtons per coulomb. And it's a proton, so we have to remember that by telling us it's a proton, we know the charge, 1.6 times 10 to the minus 19th coulombs. And finally, determine the force. So F is our unknown. So we can just do a straightforward E equals F over Q. And our electric field is 3 times 10 to the 15th newtons per coulomb is equal to F over 1.6 times 10 to the minus 19th coulombs. So our force comes out to 4.8 times 10 to the minus 4th newtons. Here it gets a little bit more tricky. So let's do what we've been doing, write down all our information before so that we can choose the right equation. How much current flows? So current, that's I, and that's question mark because we don't know what it is. Connected to 36 volts, what does 36 volts tell us? That's our voltage, 36 V, and the energy consumed is 0.2 joules. So our W is 0.2 joules in 5 minutes. Now we need to convert that to seconds. So we just multiply 5 times 60, and that gives us 300 seconds. Now we've got a problem right off the bat. We don't have Q, because we want to do I equals Q over T. Without Q, we can't do it. So we have to do 2 steps. We have to do V equals W over Q. And then we can put in our 36 volts equals 0.2 joules over Q and get our Q. That's 0.0056 coulombs. But we're not done because we're looking for I. So I is equal to Q over T. And now we know the charge, 0.0056 coulombs, divided by the time, which was our 300 seconds. And when we do the math on that, we get 1.9 times 10 to the minus 5th amps. So a little bit more tricky because this is a 2-step problem. This one is also a 2-step problem. We start out with the force. So our force is 3 times 10 to the minus 5th newtons. It says to move an unknown charge. So our charge is unknown through an electric potential difference of 1.5 volts. So we know that our V is 1.5 volts. And our energy consumed is 2.5 times 10 to the 6 joules. We know it's energy because of the joules. And then lastly, the question says, what's the electric field strength? So that's our E. E is unknown. So we can start out to get the charge by doing V equals W over Q. So that's 1.5 volts equals 2.5 times 10 to the 6th joules divided by Q, and our Q comes out to 1.67 times 10 to the 6th coulombs. So we answered the first question, but now we need to find the electric field. So that's E equals F over Q, and this time we know the force, 3 times 10 to the minus 5th newtons, and we know the charge from the equation we just did, which is 1.67 times 10 to the 6th coulombs, and rounding off that gives us 1.9 times 10 to the minus 11 newtons per coulomb. This question says, how long will it take? So how long will it take? We're looking for time. I'm breaking a lot of pencil lead here. And it says a light bulb connected to 120 volts, so V is 120 volts, and the work or energy consumed is 388,800 joules, and it tells us it draws 0.9 amps, so that's I, 0.9 amps. And what are they looking for? They're looking for the time, so we need to do V equals W over Q to get the charge first. So that's 120 volts equals 388,800 divided by Q, and that gets us a Q of 3,240 coulombs. Now we can use I equals Q over T. We know it's 0.9 amps is equal to 3,240 coulombs divided by time, and that gets us a time of 3,600 seconds, which if they ask you to, that is 60 minutes. Divide by 60. And we know that 60 minutes is 1 hour. This is a trick question. It says, what is the voltage? So we're looking for V. From a positive and negative terminal that requires an unknown force is unknown, to move 1,700 electrons, which means we can get the charge, between a potential difference of 180 volts. But it's a trick question. They're testing us to see if we know that voltage and potential difference are the same thing. What's the voltage if the potential difference is 180? The voltage is 180.